local intersection inequalities and local systems.
Yeah, thank you. I want to thank the organizers for giving me this opportunity to speak here. So today I'm going to talk about my joint work with Chertsov and Rubinstein in the last year. So this is joint work with So basically, in our work, we proved that a certain family of log final surfaces are k-stable. So basically, the tools we use are some valuative criterion developed by Chili and Fujita, and the essential thing that we use is delta invariant. We compute, basically we estimate the delta invariant for some special surfaces, and we show that the delta is bigger than 1. Then we conclude that the surface is k-stable. So basically this is our strategy. But so today's talk is going to be of 2 parts. So first I want to explain our motivation for our problem. And the second part is going to be focused on the estimate of delta variance on surfaces. And we hope that our methods can be generalized to higher dimensions, but that's some work to be done in the future. So today I'm only going to focus on surfaces. And actually there is a hidden part 3 here. If I have time, I will come to that. So, so first let me start with the motivation. So in 2013, Chertsov and Rubinstein introduced a notion called asymptotically log final varieties. So basically, we consider projective normal varieties and with a boundary divisor. And for simplicity in this talk, we will only assume that as X is smooth and D is also smooth, which contains only 1 component for simplicity. And so this pair being asymptotically log final just means that if we put a cone angle beta here, then this pair is a log final pair for sufficiently small beta. So this object also appeared in yesterday's talk, but usually in the literature, people usually let this beta to be like large. For instance, they want this beta to increase to 1. So basically, this is the program initiated by Donaldson. And but in our case, our motivation is like in the opposite direction. We want this cone angle beta to be very small. So basically, we want to study the asymptotic behavior of Klein-Stein edge matrix with sufficiently small cone angles. So I recall that in the final setting, suppose this divisor D is in the anti-canonical linear system, then we always have such a solution, right, by the work of many people. And basically, the existence of Klein-Stein edge matrix with small cone angle is not hard to establish. But for general divisor D,
Is it the base material?
yeah.
I don't think it's not hard.
Yeah. So what I mean is that for general case, the existence of small cone angle divisor is small cone angle Klein-Stein edge matrix is really difficult. At least it's not clear how to do that. So, but anyways, we can pose this question, and our goal is to study such pairs. And okay, so the first step towards this problem is first we want to have some nice classification. But in higher dimensions, this may be too much to hope for, because classify final pairs is very difficult in general. But in dimension 2, we do have a complete classification. So this is done by Chertsov and Rubinstein in their paper. And before I give you the complete complete list of classification, I just want to mention a few words about their strategy. So how do we do this classification? I think this might be quite standard. So basically, the first step is to show that the surface must be rational by using some vanishing theorem. And then we can consider -1 curves on these surfaces, and we try to contract these curves, and we decrease the Picard number so that the Picard number is relatively small, and then we can see that the surface must be either P2 or Herzberg surfaces. And then if we reduce the problem to these simple surfaces, then we can completely determine the boundary term, basically. So following this strategy, they showed that we have such a classification. Okay. Actually, in their paper, they also considered the case where the C has several components. They also have a very long list of classification. But here, for simplicity, I just assume C is just a smooth curve. Okay. So you can see from this list, basically P2 and the Herzberg surfaces are just the building blocks of asymptotically log final surfaces. You can construct all kinds of asymptotically log final surfaces by blowing up. So the picture is like this. So you have a surface. This surface might be P2 or Herzberg surface. Then you have some special curve. And then you just blow up. Pick some general points and you do blow up. And then the surface is just the blow up. And the curve C is the proper transform of the initial boundary curve. So in this way, you can cook up many asymptotically log final surfaces. Okay.
So what is EN?
Oh, EN is the -n curve in Fn. Yeah. Okay. Yeah. So now since we have this classification, then the next step is to investigate this list. We check case by case and see which one of them admits K-Einstein adjomatrix with a small cone angle. So basically, there are many ways to do this because we have some nice criterion that we can use. For instance, we can consider the automorphism group of the pair. Because if we want this pair to admit K-Einstein adjomatrix, then the automorphism group has to be reductive. So we can try to check this list and see if the automorphism group is reductive or not. So using this, we can exclude several cases from this list. And we can also use Tien's alpha invariant. We can try to compute for many cases. We can do this, and we can show that there indeed is some cases that we do have K-Einstein adjomatrix. And if we use some more advanced techniques, we can consider deformation to normal cone, something like that. We can try to construct certain test configurations for the pair, and then we can try to compute the Donaldson-Futak invariant, and we can use this to further exclude several cases, basically. So with these tools combined in 2015, Chesov and Rubinstein showed that for the list here, if we want the pair to admit K-Einstein adjomatrix with small cone angle, then a necessary condition is that the volume of this line bundle has to vanish. Okay, so this is their result. And later, by Kantor-Fujita, this result was generalized to higher dimensions. So basically, for higher dimensions, suppose we have a asymptotically log final pair. If we want this pair to admit K-Einstein adjomatrix with small cone angles, then the volume of this divisor. So it's like, so for general cases, for higher dimensions, we consider XD. And the necessary condition is that this volume has to vanish, because otherwise this thing isn't, with small cone angle, this thing cannot be K semi-stable. Yeah, you're right. But since it has volume 0, yeah, you're right. Yes. Thanks for pointing this out. Basically, the picture is like this. So I can draw. So I can put L beta to be minus kx plus 1 minus beta d. Okay. So by definition, this line bundle has to be ample. So it's in the bigger cone. So we can consider the bigger cone of the variety, and this is where L beta is. As beta goes to 0, this condition just means that the volume of the line bundle has to decrease to 0. The class has to degenerate to become a pseudo-effective class. So this is the necessary condition. Yes, you're right. There is a minus sign here. Sorry. So this is like a necessary condition. So here comes the conjecture. And so Cherenkov-Rubinstein conjecture that this is also a sufficient condition. So suppose the volume of this line bundle is 0, then the pair must also admit K-length edge matrix with small cone angles. So this is the conjecture. It's still open it's even open in dimension 2 so far. So basically in dimension 2 we can use our classification, right? We can check which one of them satisfies this condition. So it turns out that there are only 4 cases left to be considered. That's good news. So for the first 3 cases, we can easily show that this pair admits K-length edge matrix with small cone angles by computing their alpha invariant. This is also done by Cherenkov and Rubinstein in the paper, but the thing is that case 4 is still open. So let me give more details about case 4. So basically, case 4 says the following. Our surface is, we start from P1 times P1. Okay. And we take a by degree 2-1 curve. And then we pick some general points and we do blow up. Okay. So we like blow up m points. So then we take the surface and the proper transform of this 1-2 curve. So this gives us a asymptotically log funnel pair. And our goal is to show that if we put a small cone angle along this boundary curve, we want to show that this thing admits K-length edge matrix for sufficiently small weight. Okay. So this is our main object to study, basically. Okay. So my joint work with Cherenkov and Rubinstein last year says the following. So if we take sufficiently many blow-ups, say m is bigger or equal to 7, then this the statement I wrote there is indeed true. But for small m, this is still unclear. Basically, but I think we can use like similar arguments to do this, but definitely we need to work more because there's some geometry going on here in this small blow-ups. So anyway, let me say a few words about our strategy. So the first thing to think about is to use some analytic approach. So basically, at first what we wanted to do is to use Tian's 1990s work. We studied the moduli space of all these surfaces, and we try to use some continuity method argument to show that each one of them admits a K-length edge metric. But for us, it seems at least it seems to me that this approach is quite difficult because we want to establish a certain partial C0 estimate, and we also want to estimate the alpha invariant, or even the alpha m, or even alpha m2 invariant for the pair. So, and it turns out that the alpha invariant for this pair, in some cases, are not sufficient for Tian's argument to work. So basically, we have to use another approach to attack this problem. So then we turn to the algebraic side. Basically, we want to show that this pair, the log final pair over there is log k stable. Then the Yao-Tian-Donaldson for log final pair implies the existence of K-Einstein edge matrix. So of course, yeah.
So how the angle beta depends?
We want this beta to be sufficiently small, very small. Okay, so in our final proof here, like here, we just like we want to estimate the delta invariant of this pair. And to make this inequality happen, this beta should be chosen sufficiently small. And this can be how small you can determine from our proof, actually. It's not hard. So.
But when m becomes larger and larger, do you expect that this bound of beta becomes smaller and smaller?
Right. Yeah.
So there should be a uniform.
No. I mean, when m is become larger and larger, actually we have to choose beta smaller and smaller. Yeah. So as I wrote here, our strategy is to compute, to estimate the delta invariant. We want to show that the delta is bigger than 1. Then we use evaluative criterion to show that so the evaluative criterion implies the K stability of this pair. Then we have the K-Einstein edge matrix. So of course, this is a combination of many people's big, deep works. But anyways, so our problem boils down to this simple estimate, basically. So let me first recall the delta invariant. It has appeared many times in this conference, but I think this form did not appear, right? So actually, the definition is like this. We consider any log final pair, and we take a basis of the linear system, and then we cook up a Q effective divisor in this class. And then we consider the LCT of this divisor, and we define an log canonical threshold for each k, and then we let k go to infinity. So in this way, we defined an asymptotic invariant for the log final pair. So in some sense, this delta is another version of Donaldson-Futaki invariant, but it does not use the language of test configurations. It essentially only uses the information of the variety itself. So this is, but you can show that this definition is in some sense equivalent to the test configuration language, basically.
I think it's closer to English.
Right. So this delta k is in some sense a quantization for delta. So in our proof, we basically use this definition. I mean, there are many different definitions for delta. For instance, we have a evaluative definition for delta as introduced by many people's talks in this conference. But here we use this like original definition for delta. This is introduced by Fujita and Odaka in 2016. And so this is the definition we use. And the criterion says the following: if the delta is bigger than 1, then the log final pair is uniformly k-stable. So this result is the combination of many people's work. So here I only list a few. And for our problem, our goal is the following: we want to show the delta is bigger than 1 for sufficiently small. So how do we do this problem? The question boils down to the following: how do we compute, or more precisely, how do we estimate delta invariance effectively? Luckily, there have been many.
Wait.
Uh-huh.
I think the theorem is due to the first principle. If I remember.
Oh, yeah. Yeah, because in Bloom-Johnson's paper, they did not include the boundary term, right? But
I think they do. Right, they don't, but essentially
yeah.
Same argument.
Yeah.
It's in your thesis. Yeah.
Yeah, so,
It doesn't match.
We're all friends.
I mean, the argument works with data.
yeah, of course, yes. But this statement appears in this.
Yeah, but
Yeah.
just because they didn't complete the case, so we write it down for the sake of the same argument.
Yeah, I agree. Okay. So in the literature, there have been several important progress in this problem. Basically, the first attempt to compute delta invariant was made by Park Wang, I believe, in 2016, and they estimate the delta invariance of all smooth del Peso surfaces. So this gives a purely algebraic proof of Tian's theorem, and their methods is by looking at the Newton polygon, because in dimension 2, it's still, in some sense, the Newton polygon is still controllable, basically. So, and for toric case, there is a nice formula obtained by Bloom-Johnson in their paper, and basically their formula says that for toric varieties, the delta invariant is just determined by the barycenter of the polytope of the variety. So that's some progress in the literature. But in our setting, we have this annoying boundary term, and this is causing big troubles for us. Because as you can see, if we let beta go to 0, then this boundary term will become worse and worse. By worse, I mean the coefficient of the boundary term is closer and closer to 1. So if we want to show something is log canonical, then we have to take a very careful treatment for this boundary term, basically. So to do this problem, we have to look for some like the approach we use is like more traditional. We want to use some traditional estimate for LCT on surfaces, and then we want to combine with other techniques from the literature. So this is our basic strategy. So first, let me recall some classical ways to estimate LCTs, especially for surfaces. I think this is well studied, and there are many basic tools. Here I only list a few. Like the first thing is inevitable, because we have to compute intersection numbers everywhere, right? So the second thing is a powerful tool, which is the inversion of the junction. And on the surface, it has a very nice form, which I will show you in a second. And we also use multiply ideal sheaves to consider the locus where the divisor is not KLT. But in our problem, we do not use this ideal sheaves tools. What we essentially use is inversion of the junction, basically. And so on surfaces, inversion of the junction takes the following nice form. So suppose we have this complex surface. Suppose we have an effective Q divisor. If we can decompose this divisor into two parts, say C is some smooth curve, and A is a coefficient that is not bigger than 1. And suppose this pair is not log canonical at some point, P. Then the inversion of the junction says that first, the multiplicity of this divisor at this point has to be bigger than 1. And the second is the most important one, is that the local intersection number of C and omega at this point is bigger than 1. So this is basically like the most powerful tool for computing LCT on surfaces. Basically, in our argument, this is essentially what we use. Okay. But of course, we have to use some more tools, because delta invariant is something that defined in a way that's very different from alpha invariant. Because if we want to compute alpha invariant, basically what we want to do is to first we wanted to look for some bad divisors, and then we compute its LCT. Then we argue that the divisor we found is the worst. There's no more other divisors that giving smaller LCTs. So we can compute the alpha invariant by looking for the worst divisors in the linear system, basically. But for delta invariant, this is not going to work, because from the definition of delta, you can see that we have to take a basis of the linear system, and we add them up. So especially if the multiple k is sufficiently large, then this divisor is very difficult to describe. Basically, we cannot control the behavior of this divisor. It's very complicated. And so this is a big difference between delta and alpha. And so we need to look for some other tools to control the basis divisor. And so there's a nice thing that we use, and this is the volume of divisors. And we want to use the volume of divisors to do some multiplicity estimates. Then we can use some other new local intersection inequalities to estimate our delta invariant. So let me explain these new tools with more details. So the first thing is the volume of divisor. That's a key concept in our computation, basically. But of course, this notion is quite standard. So let me just briefly recall. It just measures the asymptotic of the dimension of this linear system. So one thing to keep in mind is just that suppose the divisor is NAF, then the volume is simply given by the top intersection number. So this is the standard fact, I think, from Riemann-Roch. And we say the divisor is big if the volume is positive. So all these are standard notions, I believe. So the nice thing of the volume function is the following estimate given by Fujita and Odaka, I think. And in their paper, they prove the following. So suppose we have a k basis type divisor of the line bundle with k sufficiently large. Then consider any prime divisor over x. If we pull back this divisor upstairs and we measure the vanishing order of the basis type divisor along F, then we have this nice estimate. Okay. So this quantity is quite important in the study of k stability in the literature, because and this quantity has a name. It's called the expected vanishing order of L along F. So this, in some sense, this quantity measures the vanishing order of the class along any divisor. So basically, we use this estimate. And one thing to note is that this estimate is basically sharp, in the sense that if we let k go to infinity, we can always find some specific basis type divisor, which is kind of induced by the filtration of this F. We can cook up some basis type divisor such that the multiplicity of this divisor along F is almost this quantity. So in this sense, this estimate is sharp. And we use this estimate quite often in our computation. We use this to control the multiplicity of our basis type divisor along all the locus of the surface, basically. So this is an important step in our problem. So we apply their estimate to our problem, and in our setting, so this is our setting. We have this surface and a boundary curve, and then we take a k basis type divisor D, and the goal is that we want to show that this pair is log canonical for some number to be determined, for some number bigger than 1. If we can do this for sufficiently large k and sufficiently small beta, then we are done, right? From the definition of delta invariant. If we can show that this pair is log canonical, then the delta invariant is bigger than 1 for sufficiently small beta. So this is our goal. And the thing is, we use this multiplicity estimates, and this is an example. So since we have done many blow-ups, and so there are many exceptional curves. For instance, we can control the vanishing order of the along exception divisors by just using the formula. We can just compute. It's elementary computation, but one needs to be careful because in this computation of volume, if the number x is large, then it's possible that this divisor is no longer nav. So if we want to compute the volume of a non-nav divisor, we have to subtract some negative divisor. We have to use Zariski decomposition to replace the line bundle by some nav line bundle, and then we compute the volume, basically. But I think this is standard. So by explicit computation, we can show that, for instance, along the exception divisor, the multiplicity is bounded by this thing. So from this, you can see that the multiplicity estimate depends on beta, and also depends on m. M is the number of blow-ups. So this m plays a role here, and there are some higher order terms. And
by exceptional, in this example, you mean none of the -1 curves that intersect C?
yes, just some curve like this, some curve here. Yeah. Okay, so as you can see in the estimate, there are many parameters like the number of blow-ups, beta and k, and there is also a lambda here. So you can see there are many parameters to play with, and all these are important in the final argument because basically you can see from here, you can see this pair. Here we have a very bad boundary term, 1 minus beta times c. If beta is sufficiently small, this boundary term is in some sense quite large. It's very dangerous to live near this boundary curve, right? But on the other hand, as I draw here, if beta is sufficiently small, the positivity of the line bundle is becoming smaller and smaller. So the basic type divisor is coming from a very small ample line bundle. And in this sense, so in some sense there is a competition going on here. So this is something small, but this is something large. We have to compare these two things, and we have to choose beta and m and k in a suitable way to make this pair log canonical. So basically.
Did you squeeze this bound from the previous bound?
Yeah. Yeah. You mean this bound?
Yeah, or do you deduce this bound from the previous bound? There is this general bound by virtue of that.
Yes. We use this. Yeah, we use this. So here we just plug in L beta, and here we choose F to be the exceptional curve E, and we compute this integral. Yeah. You can just compute this explicitly here, and this is the result of the computation. Yeah.
So in your result that you put at the very beginning, that you can only do it for n bigger than 7.
Yes.
Because of this effect.
Yeah, this has this in some sense this explains why we have to restrict our m, because if m is not big enough, then the multiplicity in some sense is gonna screw you up basically, because this, as you can see from this, it's a subtle thing to show this is log canonical because.
So the formula, this formula is still 2 if n is 6 or 5.
Yeah, this estimate is actually true for any m. Yeah.
So in intuitive
1 has to be 1. And delta is 1. Everything is 1. Delta is 1 by everything is 1. We need bigger than that. So it means we need to estimate the linear term in this. Linear term in this is very important. It's just like it's like you have delta everything and you're discussing the
I understand this kind of individual that you can do from 7 onward, you can do just to 1.
No, because if, for example, if m is 1, delta cannot be, delta is most 1. It's automatically in some cases. So it's quite sharp.
Yeah. So this estimate is subtle. We have to estimate the linear term in beta. And the higher term may not be so important, but the linear term is very crucial to show the log canonicity of this pair. Yeah. So, okay, now let's come to this local intersection inequality. So basically now our pair is this one. So for instance, let's look, let me do an example for you. So suppose we want to, suppose we are looking at this, locus. So suppose there is an exceptional curve here, and this is our boundary term 1 minus beta times c, and there is some basis type divisor lambda times d, something like here. So we want to show that this pair is log canonical. So basically, a standard way to do this is first we decompose this lambda d into 2 parts, because the basic type divisor may contain some components of the exceptional divisor. So we can write it as some components, some multiples of e plus something that we cannot control. So we can suppose this, and by the estimate here, we know that this A is bounded from above by this estimate. And now the pair just becomes as 1 minus beta c plus e times e. So we want to look at this pair near this point, say this point, let's call it P. Okay. We want to show that this thing is at least log canonical at this point. Basically, we need to look at this pair at every point along this curve C. But here, I just use this as an example to show how we use this estimate. So here, suppose we are living near this exceptional curve. Then we can decompose the basis type divisor into 2 parts, and we write our pair in this way. And suppose we argue by contradiction. Suppose this is not log canonical. We want to not log canonical at P. We want to try to find some contradiction from this assumption. So suppose this is not log canonical, then what we can use is some local intersection inequalities that I'm going to introduce. So yeah, for different divisor, it's might be different, but it's not important in our case, because eventually we will let k go to infinity, and this term will go to 0, basically. Yeah, you're right. This is basically coming from this estimate, because here, to be more precise, this the bound for this multiplicity is actually should be a sum of should actually be something like this. Basically, we are looking at this this thing, and we let k go to infinity. Then we will the dimension of the vector spaces will converge to the volume. So a priori, this epsilon k is not clear. How it's determined is not clear. But I believe in Bloom-Johnson's work, they have some uniform estimates for the approximation, right? So, yeah. It also depends, I think it also depends on the class of the line bundle, and I suppose.
Also, E here, you only have finite many choice, and the class is somewhat determined. So maybe that's the reason about it.
Yeah. Okay, so this is our pair. So as you can see, we have like 3 terms. We have 2 curves intersecting at this point P, and we have something left. And we want to study this, something like this. So we can use some local intersection inequalities developed by Chestov. So in 2013, Chestov proved a statement like this. So suppose we have a surface, suppose we have 2 curves intersecting transversally at one point, and there are some other divisor that we don't know about. And the thing is, suppose this thing is not log canonical at P, then we can deduce some intersection relation, some intersection inequality from this assumption. So basically, this estimate is obtained by blowing up. You just blow up this point, and then you apply inversion of the junction, and then you keep blowing up. So it's like an inductive argument. You can show that if this pair is not log canonical, then you have some nice inequality that you can use. So here we can also apply this inequality to our case, because we are basically exactly in this situation. We have 2 curves intersecting at one point, and we have something that we don't know about. But suppose this thing is not log canonical, then we can use this inequality to derive some contradiction, because on this surface we can explicitly compute the intersection number, and we can try to get a contradiction from this conclusion. So basically, this is the philosophy of our argument. And if we use this, we can show that for sufficiently small beta, the delta event is bigger or equal to 1. For m, bigger or equal to 5. Okay. So, but the bad news is that it's bigger or equal. We did not achieve strictly inequality. We only showed that it's bigger or equal. So it just means that the pair is log k semi-stable. We want k stable. So we still have some work to do. But there's a reason for this, because in this local inequality here, as you can see from the statement, the curves C1 and C2 are symmetric in the statement. And the final conclusion is also symmetric in C1 and C2. So in this sense, this statement, so here C1 and C2, really there's no difference between them. But in our problem, there's a big difference, because the boundary curve C and the exceptional curve, they play different roles in the geometry. So if we use this symmetric inequality to take care of this problem, it's not, in some sense, it's not going to work. So we have to develop some asymmetric inequality. So that's what we do in our paper. So what we do is that we develop the following local intersection inequality. This statement is specifically designed for this problem, but we believe this also has some applications in some other problems as well. But in this statement, we just write this as in a way that we can directly apply this to our problem. So we have this boundary curve 1 minus beta c, and some other curve az, and here the number a can be controlled by the multiplicity estimate, as I mentioned before. And there's something left here. And suppose this thing is not log canonical, then the conclusion is that we have some inequality that we can derive. So if we use this inequality, and then we can try to derive some contradiction from this assumption. So we can conclude that this thing is indeed log canonical near this point P. So basically, we do this kind of argument for all kinds of points along this curve, and finally we can achieve that the delta invariant for this pair is bigger than 1. But we have to make this m to be bigger or equal to 7. So as I mentioned, in this estimate, there are many parameters to play with. There's the the number of blow-ups. There's a cone angle m here. There's also the k here, and there's a lambda here. Actually, all these constants are important to make this inequality to hold. Because for instance, in our final result, actually what we choose is actually we can choose lambda to be 1 plus beta over 100. I think this is what we chose in our paper. So basically what we prove is that delta for this surface is bigger or equal to 1 plus beta over 100 for sufficiently small beta. And yeah, so there's a few words about delta invariant, and so this is not related to our to the thing that I talk about. So when I was working on this this project, I got quite interested in this delta invariant, and it turns out that in Bloom-Johnson's paper they have very nice formula for the delta invariant on toric varieties, and they prove that for toric final manifolds, their formula is exactly the same formula obtained by Chi for the greatest rich lower bound. So it's natural to think that on final manifolds, indeed, the greatest rich lower bound and the delta invariant are the same thing. So then I try to show this, and it turns out this proof is not so difficult if we use some deep results developed in the literature. For instance, to show this on final manifolds, we have like to approximate the greatest rich lower bound by a sequence of conic Ke matrix. And on the other hand, we have to approximate this delta by a sequence of delta invariants with boundary terms. So basically, it's like this delta can be approximated by a sequence. And on the other hand, the greatest rich lower bound can be approximated by a sequence of conic Ke matrix with cone angle along this divisor. So then you can use the Yaotian-Donaldson for conic matrix, and then apply the evaluative criterion of Zhili and Fujita. You can show that this is indeed true. So I just want to mention a nice corollary of this observation, and it's the following. So in the paper of Park Wang, they proposed a conjecture. They conjecture that for any two final manifolds, the delta of product is just determined by the minimum of delta x and the delta y. But if we use this, then we can show that if the delta of one of them is smaller or equal to 1, then this is indeed true. The reason is very simple, because from an analytic point of view, the beta for product manifolds this is not hard to see just from the definition, because you can take the product metric of different two manifolds, and so this direction is basically very simple from the definition. But on the other hand, if we look at delta invariant, if we look at the definition of delta invariant, the other direction is not hard to see, basically.
Sorry, for the first inequality,
Mm-hmm.
You also need to consider product, non-product metric functions. So how do you
Do I need? So you just take a metric from here and here, then you take the product, and you will get.
So then you get to the other. Oh, okay.
Yeah, so this is clear from analytical point of view, but this is also clear from algebraic point of view. If we combine these two things and we use this relation, we can show this very easily. But for general case, suppose x and y, the delta of x and y are both bigger than 1, then this is still unclear how to show. But if one of them is bigger or smaller or equal to 1, then both are equal to beta. So one can show that this equality actually is true. But for general case, I think there's still something missing. Maybe we have to use some non-Archimedean geometry or something like that. But anyway, this gives at least a partial answer to a conjecture of part 1, I think. So I think I'll stop here.
Any questions?
So at the beginning you said that you saw the conjecture, or rather the conjecture was solved in all cases apart from yes, n between, I presume, 1 and 6. Is that correct? Or am I missing something? I mean, is it still open?
It's
for any 1 and 6?
yeah, still open.
So what strikes me is, do you take n equal 1? Is it story?
Yeah, there are some automorphism groups there, so we cannot directly apply delta invariant because we can at most get 1 for delta. If we
It's not only German. In some cases, but in some cases of the German action, so delta is not 1, so this is why this must be.
Delta is not 1.
That would be 1 using 0.
This is pretty nice.
More questions? Okay, let's have the code.
Okay, and I think as usual it should be food in that room.
So next talk will be 306, right?
Next talk will be 306 and third floor.
I didn't have this.